acetylcholinesterase. Okay. Last time we discussed the agonist at the cholinergic receptor, particularly the muscarinic receptor. And then tomorrow we'll discuss the antagonist. So we'll be able to recognize the structural features of the antagonist. But today we'll discuss sometimes what are called indirect acting agonists because they prolong the action of acetylcholine in the nerve junction, right? If we're having a compound that inhibits the enzyme acetylcholinesterase that breaks down acetylcholine, we're going to prolong the duration of action of acetylcholine in the nerve function, the nerve terminal. Now there's another enzyme that also is a cholinesterase called serine-cholinesterase or butyrylcholinesterase. This has a pretty broad substrate specificity, so that's a little different enzyme. But the one we're talking about is acetylcholinesterase. Okay, so it prolongs the lifetime of acetylcholine because it prevents the hydrolysis of acetylcholine. So how does it work? The active site has a lot of amino acid residues, which you're already familiar with. We have two imidazoles, two histidines. The central player is this nucleophilic primary alcohol of the serine. Okay. And this glutamic acid works together with the histidine here. And then we have the tryptophan, the electron-rich indole ring of the tryptophan to help position acetylcholine in the active site. And then you'll see the water. There's always water in enzyme active sites as well. So if we position acetylcholine, remember the structure, we have the trimethyl ammonium, we have a quaternary nitrogen, and then of course what we're interested in, the chemistry here, is the ester hydrolysis. So this enzyme is a catalyst for the hydrolysis of that ester, the acetate ester. So how does it position itself? Well, we get the cation pi interaction here with the indole and the positively charged quaternary nitrogen. Then you see the serine hydroxyl becomes more nucleophilic because hydrogen here forms a strong hydrogen bond with the imidazole, which in turn is interacting with that carboxylate. So there's kind of electron sink in this direction. So it becomes more nucleophilic. Then the carbonyl carbon, this carbonyl of the ester functional group becomes more electrophilic because of the interaction here, the strong hydrogen bond with this imidazole, which is in turn connected with the water. Okay? So that arrow then represents the attack of the alcohol on the carbonyl. Of course, we go through a tetrahedral transition state, and then that collapses to form we'll see the product. Basically, this is a trans-esterification reaction, which means you start out with one pair of alcohol and ester and end up with another alcohol and ester. So there's an interchange taking place. Attack of serine hydroxyl on the acid. Any questions about how it's kind of sitting in here? So the alcohol, the serine alcohol is made more nucleophilic because of this hydrogen bond interaction. The carbonyl is made more electrophilic because of this hydrogen bond interaction. That's what enzymes can do. They can sort of act as acids and bases in the same reaction flask, if you will, right? that's the reaction. Then what are the products? The products are choline. You see, now the ester has been hydrolyzed. And now the serine hydroxyl, remember it was attacking that ester. And then after the collapse of the tetrahedral transition state, we get an acetate ester now at that serine hydroxyl. It's no longer an alcohol, it's an ester. So this is what we mean by transesterification. If you go back to the first products, we saw we had an alcohol and an ester, right? And now we have an alcohol and an ester. Transesterification. So chemists call this transesterification. So the enzyme basically carried out a transesterification reaction. But this isn't the end of it. We have to get the serine ready for the next cycle, right? Because the serine, it's not a serine anymore, it's an acetate ester of that serine hydroxyl. So we have to regenerate the active site. Okay, how is that done? After the water comes in here, it's activated by the hydrogen bond. So it'll attack the acetate ester that's formed on the serine. So in the end, we get, basically we just get acetate, right? Or acetic acid is product formed as it diffuses away. That acetate diffuses away, and then we're back to the starting point. That's the regeneration. Okay, why did I make a point about this regeneration? Well, it occurs very rapidly in this catalytic cycle for acetylcholine. It's a microseconds. So the whole cycle is over in a very short time. But for some of the inhibitors of acetylcholinesterase, this regeneration step takes minutes, or we'll see even hours. So this regeneration reaction is fast here for the acetate ester at the serine, okay, but it would take a much longer time when we expose the acetylcholinesterase to some of these inhibitors that we'll see in a minute. Okay? So that's the regeneration. So this is the end of the catalytic cycle. We have to reform the active site again. Okay? There's bonds that are made and then broken in the catalytic cycle. All right. Any questions about that? That's the enzyme how it catalyzes the ester hydrolysis of acetylcholine. Okay, so then we'll look at the inhibitors of acetylcholinesterase. Okay, how do they work? Well, keep in mind that we've just gone through the catalytic cycle, so now we understand how the enzyme works. These are the two general structures of the inhibitors of acetylcholinesterase. First, we have aryl carbamates. Remember carbamates? The oxygen, carbonyl nitrogen. They're intermediate in stability between an amide and an ester. Then we have phosphate esters. So esters of phosphoric acid. X is a leaving group in the structure of the inhibitors. So what happens then? Well, first of all, this phenyl ring prevents the interaction with the muscarinic receptor, so these are not agonists. So they can't act as agonists. We're talking about inhibitors of acetylcholinesterase. So here's the serine hydroxide. Remember, that's that central amino acid residue that attacks the ester carbonyl of acetylcholine. So what happens if we expose the acetylcholinesterase to these inhibitors? Well, the serine hydroxyl will attack. It's kind of positioned in that active site because